Hello everyone. In this video we are going to look at the equations of motion for the SCARA robot, the robot that we use typically for assemblies. SCARA stands for Selective Compliant Articulated Robot for Assembly. And here we are not going to include any actuator dynamics, so we are not going to include the equations for electric motors and the gearboxes, and no static friction. So the only friction we use here is viscous friction. And we just consider the effect of those actuators as torques tau 1, tau 2, the force F3 for up and down motion, and the torque tau 4 for the final twist angle. It has 4 degrees of freedom, theta 1 and theta 2, and then D3 and theta 4. Here we just call them Q1 to Q4. And the centroids of the members, the first member, the blue one, the second one, the green one, the third member, the up and down motion, and the last one are shown by G1, G2, G3, and G4. And the base frame is shown over here for you. So now I'm going to show you the overall derivation of the equations of motion here in one note, but then to get the final equations, we go to MATLAB and use MATLAB symbolic to do all the differentiations for us. So each member here, you can say that it has a translational kinetic energy and a potential kinetic energy. Although for the first member, this blue one, you can say it only has a rotational kinetic energy about this axis, not about its centroid. But if you want, you can just add the two terms for each and every one of them. So the rotational term is, as you know, 1/2 I omega squared, or in terms of matrices, if you wanted, it is 1/2 times what? It is 1/2 times omega transpose, right? And then what? You have here your I, and then times omega. But this I here is about a body attached frame. Here we're going to write everything in the base frame. So this I that you have in the body attached frame, I about G, you have to transfer it to what? To the base frame. So what you will use is RR transpose, right? So you have this rotational term for each one, and then the translational term is simply 1/2 M times V of that centroid squared, or if you want to write it as vector, it is going to be V of the centroid transpose times V of the centroid. Okay, because here everything is three-dimensional, so you can write it like that. And as long as you find these two and add them together for each and every one of the members, the total kinetic energy is what? Sum of all these terms here. And the potential energy here only comes from gravity, so it's simply MIG times Z of each member. And Z here is the vertical direction that is against the gravity. So in order to find the V's, we need to find the location of the centroid and then take time derivative for that. So the three parameters that are involved for the geometry of the robot here is this offset D1, and this length L1 and length L2. These are the three parameters that here we have included. We can add more, but this is enough for a simplified derivation. So clearly, the location of G1 in the base frame is what? In the X and Y axis, if the rotations are measured from the X axis, clearly it is going to be L1 cosine of theta 1 divided by 2, and this divide by 2 is because we assume that the centroids are in the middle of the members, and then L1 sine of theta 1 over 2, and then D1. Here also we neglect the thickness of the members. Okay, so the thickness says, or what? This thickness of members are neglected. If you want, you can add them, but here we just we neglect it because they affect the potential energy. So if we go here, and D1 is basically the elevation of the centroid. Again, here we are neglecting this thickness. Take a time derivative with chain rule, you get negative L1 sine 1 Q1 dot over 2, L1 cosine 1 Q1 dot over 2, and 0 because D1 is constant. Omega of member 1 in 0 is simply 0, 0 Q1 dot because the rotation is happening about the z-axis. Rotation of member 1 in 0 is simply a rotation z with angle Q1. And here we assume that these members are slender. So another thing that we have, that thickness of the members are neglected. The other one is the members are considered as slender bars. Here I just added those assumptions for you. As I said, there is only viscous friction, the thickness of the member is neglected, and the members are considered as a slender bar. So for the first member, if the mass of it is m1 and the length of it is L1, the only moments that we have is IY and IZZ, and in this case, and here when I talk YY and ZZ, these are with respect to the body attached frame. Pay attention that this is what, this IG1, this is not really with respect to 1. There is a typo here I need to correct for that. This is really not with respect to 0, this is with respect to 1. This is with respect to its own body attached frame. Remember in DH, we had the x-axis along the member, and then y was in this direction, right? So this was like y1, this was x1, and z was out of the plane. So we are calculating with respect to this frame, the I. If the thickness of the member is a small, slender, I about x is 0, I about y and z is ml squared over 12. Okay, that's what you see, this one. When I pre and post multiplied by r of 1, 0, that whole thing now becomes I of G1 in frame 0. This one is I of G1 in frame 1, okay? So this is what, these are the information we need in terms of omega, r, I, and v for member 1. Now for member 2, the coordinate of the centroid is clearly what? It is L1 C1 plus L2 over 2 C12, L1 S1 plus L2 S2 over S12 over 2, and again D1, and again here we are neglecting this small thickness. And we take time derivative again, and we get these guys. We have done this for 2DOF if you watched my previous videos. And again, this is IG2 with 2, not 0. The same slender bar assumption. The mass is M2, the length is L2. And omega 2 here is Q1 dot plus Q2 dot. R20 is rotation Z of Q1 plus Q2. Then we go to member 3, the red member here. If you look at the red member, the coordinate for the centroid of it is the coordinate of what? The end of member 2, the end point of member 2, and also it has this D3. So if you look at that, L1 C1 plus L2, you see here it's not L2 over 2, it's the entire L2, C12, L1 S1 plus L2 S12, and then D1 minus Q3. Okay, because Q3 positive direction is considered downward, so when it's positive, it's going to go down. So it's going to be like that, and then this is also R of G4 if we neglect what? This dimension here. If we neglect this dimension. If you want to include that dimension, you can give it some parameter. It doesn't matter. You can give it another parameter here. You can call it, I don't know, some D4 or something, or L3, for instance, a constant, right? And then that is going to be basically this one here, and then minus L3. Okay? Yeah? But when you take derivative, you see here, D1 has no effect. It becomes 0. That L3 also becomes 0, and therefore, it is not going to affect this component. This component is just going to be negative Q3 dot. You might say it can affect the potential energy. Sure, it can, but remember, when we write the Euler, the Lagrange equation, what is the Lagrange equation? It is d over dt of partial of L with respect to Qi dot minus partial of L with respect to QI equals capital QI and non-conservative. And L, as you know, is clearly kinetic energy minus potential energy, Lagrangian. So here L, here that L3, that fixed distance L3, you saw that it has no effect in kinetic energy because it did not show itself in the velocity of 0.3 or 4. So it has no effect on this. On this one it does because it is going to affect the z of 0.3. So it is going to affect this, but we are not going to directly use potential energy here. We are using derivatives of potential energy. So if I add some constant to this, right? If I add some constant c to this, here, this is partial of k with respect to qi minus partial of L with respect to qi. Clearly, adding a constant, P, not L. Clearly, adding a constant to P is not going to affect this term. So you see, adding a constant is not going to make any difference here. And so here we just neglected it. But again, if you want, you can go ahead and physically add that. It's fine. So going back, that is the velocity of 0.3, and that is also the velocity of 0.4, right? Because they're attached together, they go up and down together. And I of members 3 and 4 are again considered like this. Now here, I did not consider length for these members 3 and 4, so I'm not going to use ml squared over 12. I just gave them a fixed number of iz z3, and this is iyy3, but here I assume they are equal. They might not be. And here, you see, I only gave them y and z, and I assume that they are equal. Again, they could be not equal based on their mass distribution, but here I just, for simplicity. Omega of member 3 is the same as omega of member 2 because member 3 is only going up and down, so it has no extra rotation compared to member 2. Omega of member 4, though, is q1 dot plus 2 dot plus 4 dots if we assume that the z4 axis is upward, right? So it's going to be plus 4 dot. If the z-axis is downward for the fourth axis, for the third axis, then we can say what? We can say that it's minus q dots. Okay, so here it could be plus or minus depending on which direction of axis we consider for the fourth axis. And rotation of member 3 is the same as rotation of member 2. And rotation of member 4 is a rotation z for angle q1 plus 2 plus 4. So now I have all of the v's, all of the omegas, all of the r's, and all of the i's figured out. So all I need is to plug them here into this relation to find k and to find p, subtract them to get L, plug them here, and get these partials, right? And what are the Q non-conservatives here? So the only non-conservatives we have are these actuations, F3, tau 1, tau 2, tau 4, as well as what? The viscous frictions. So if we want, this is going to be what? This is going to be basically either tau I or Fi, right? One of them. And then minus what? Bi times Qi dot, right? The viscous friction. Okay? So these are going to give me 4 equations because here I goes from 1 to what? 1 to 4. So I will get 4 governing equations. And I also will derive for you the D matrix and the C matrix. So you know your total form of governing equations are like D of Q times Q double dot, correct? If you write it in vector format, plus C of Q and Q dot, the Christopher symbols matrix, times Q dot, and if you want, you can bring that BQ dot to the left-hand side, so it becomes plus B matrix, which is diagonal of the BI's. So if you want, you can write it as diagonal of the BI's times QI dot times Q dot, right? This is equal to what? The tau. If we neglect the static friction and if we neglect what? The actuator dynamics. So here I'm going to derive for you the D and I'm going to derive for you the C. And the way I derive the D is, if I get my equations, there are two ways that you can derive D. One is you can directly set your kinetic energy, this total kinetic energy, you can directly set it to what? Set it to basically 1/2 of vector Q dot times D times Q dot, and this is Q dot transpose, and then set them equal and find D. Or you can find D directly. For that, you need to find these components of Jacobian, JVI and J omega I. You can watch my video on the 2DOF when I explained the Lagrangian derivation of equations of motion. I explained these. So for that, you need to find the Jacobian, you need to do forward kinematics and find the individual Jacobians and the upper and the lower portion of them to find D. So you can do that as well. Here I'm going in a backward direction. So I'm not directly finding D. I find the equations, and then through the equations I'm going to find D. Because if you expand this, right, for the ith equation, what is it going to be? This one is going to be summation of D ij, summation j goes from 1 to n, in this case 1 to 4, of what? Qj dot, double dot. Okay, yeah, that is going to be this one here. So if I want this dij, what should I do? All I need to do is to take partial derivative of it. The left-hand side of this equation, if I call the left-hand side of this equation, left-hand side of the ith equation, if I call it something, call it like LHSQ1 or EQ1, something like that, call it a variable, a symbolic variable. If I take partial derivative of that, with respect to what? With respect to Qj double dot. That is going to give me Dij. You see, so I have 4 equations, I have 4 Q double dots, so I'm going to get 16 of these D's, which I'm going to arrange as the 4x4 D matrix. And once I have the D's, I can find the C's, the Christoffel symbols, and if you remember, Cijk was what? Was 1/2 of the partial derivative of I and K with respect to Qj, and plus the partial of Djk with respect to Qi, and then minus partial of Dij with respect to what? With respect to Qk. So once the D is determined, I can get what? All of the individual C's, and then I can arrange them into the matrix C. So let's go ahead and look at the code that I wrote, and I'm going to share them with you, right? You see it's about 140, 50 lines. So here I define everything symbolic, okay? And these Q1 dots and 2 dots, later I used to write my D's and C's a little bit nicer, but I don't really need them. All I need is to define T, Q1, 2, 3, 4, all as time variables. And then I also need to define G here. And G does not really need to be symbolic here, right? G does not need to be symbolic. Even the T's and F's, they do not, because I'm going to use numbers for them directly. But if you want, you can have them as symbolic, right? Even the M's and the I's and everything. But here, since I have some of my numbers already, I can get rid of this portion, okay? I don't really need them to be symbolic. So Here, those parameters, the geometry is defined, the inputs are defined, and here one thing I want to explain is the force that I got for member 3, assuming that the force is coming from a motor and the motor is moving a rack and pinion to move the member up and down. Here, this 8 is the torque of that motor, T3, and divided by what? The radius of that pinion that is driving the rack. This is going to be the force that is applied to member 3 if we neglect what? If we neglect the inertia of the pinion, okay? So here 30 Newton meter on member 1, 10 on member 2, 8 on motor 3 that is driving the member up and down, which here corresponds to 800 Newton up and down force, and 6 Newton meter on member 4. These are the masses and the moments and the moments of inertia that I have for members 1, 2, 3, and 4. And G, here are the coordinates of the centroids of all 4 members, the way I define them for you, right? And these are the viscous coefficients of friction on the joints 1, 2, 3, and 4. Okay, I did not even use all the same. Here are my inertia matrices. These are my rotation matrices, the same way I defined them. These are my omegas. The V's, you see, they are the time derivative of the R's with respect to time. They are the time derivative of the R's. K is simply adding all the translational and rotational terms. P is simply adding MGZs. L is subtraction of K minus P. And here you see that this is the derivative of L with respect to Q1 dot, right? Partial of L with respect to Q1 dot, and then time derivative of that. That is this first term here. Look, that is basically this one, this first term here. That is this guy. The next one is what? The next one is going to be partial of L with respect to Q, and that is this one here, of course. You see here I have done it for, this is equation 1 left-hand side, equation 2, 3, 4, 5, 3, 4. And then my total equation is what? Is the left-hand side VPA 6. What is this for? As you know from my other videos, this is to convert all of those nasty fractions of symbolic that you can see right here. You see all those fractions, 702 over 30, 125, to convert them into decimals. This is equal to T1, the torque, minus B1 times Q1 dots, right? The total non-conservative force or torque on it. And similarly, I get all of these other ones. Why did I separate the left-hand side from the whole equation? Because later I want to use those differentials that I just explained to you, this one. I want to do this part here, look. I want to take partials of the left-hand side with respect to Q double dot to get my D components. And here you can see that this is how I got all of my D's. If you want, you can automate this as well with a nested for loop. But if you do that, this is your D matrix. Look, that is your D matrix. Then what I did was I put all of Q1, 2, 3, and 4 into Q vector and all of the dots into Q dot vector. Then I carried the formula for the crystals symbol here, which is, I just showed you. This last one down here, I carried this formula, right? So I carried this portion here, and you can see that again down here, right? And I need to use 3 nested for loops. I, J, and K go from 1 to 4. And if I do that, now look, I can get what? I can get my crystal symbol matrix C, which has the centripetal and Coriolis terms. Okay, and then here I basically because you're gonna get 4 times 4 times 4, you're gonna get 64 C's. So you have to multiply those C's by the corresponding Q dots to combine them into the C matrix. So just finding all of the 64 C's does not mean you found the C matrix. Because C matrix, as you know, is a function of what? It's a function of q and q dot. So theseCijk's are multiplied by some q dots. And I told you in my previous videos how to combine them into a matrix, right? So that's this video here, equations of motion for n-linked robot in the jointed space using the Lagrangian formulation, which is under my playlist robotics. Here I show you how to basically use these double summations and combineCijk's with q dots to form what? To form different basically rows of the C matrix, okay? So you can go to this time about 1 hour, 1 minute or so, and it is completely explained how to form your C. And clearly you see in C there is Q and Q dots. And now that I got my equations, all 1 to 4, this was all derivations. Now what are my equations? I guess they are shown here. If I move a little bit to the left, you should be able to see my equations, right? This is equation 1, right? This is equation 2, and this is equation 3 and 4. So you see my governing equations clearly here, right? And some of them are long, like this one, right? You can click under each one, and it can show you all the way. Now here, there are tons of decimals are used. But these are the 4 governing equations. Okay, now that you got your governing equations, it's time to do a numerical solution, because these equations are highly nonlinear. You cannot solve them directly. There is no analytic solution. So we have to convert these analytical differential equations to ODE45, but ODE45 needs first order ODEs instead of second order, and it needs function handles, not symbolic functions. So I need to do both of those things. Here you see I combine all of these 4 symbolic ODEs into a vector, and then I pass it to this reduced differential order method in MATLAB, this function. If you give it the variables and if you give it the equations, it will break it down into first order ODEs. So here 4 first order ODEs are going to be converted into 4 second order ODEs are going to be converted into 8 first order ODEs, and the variables, the dummy variables, you can see them. They are Q1 to Q4 all the way, Q1 dot to Q4 dot. Then once the first order ODEs are written, you have to write it in a form like a matrix M times all of the Q dots, all of these, the derivatives of these variables, equals the right-hand side. Here, that coefficient matrix is M, the right-hand side is F, and you can see that here, right? The good thing about the live script is as you move your cursor over each variable, it shows you what that variable is. And then you invert the coefficient matrix, multiply by right-hand side, or you can use a backslash and get F here. F is all of the double dots. Now, these are the right functions to be passed to ODE function, and ODE function will convert your symbolic functions with symbolic variables into function handles, ODE fun, which now it can pass to ODE45. Here I use all 8 initial conditions of 0 and solve these ODEs for 5 seconds. And then I plot the solution Z has 8 columns. I plot the first, second, third, and the fourth column, which corresponds to Q1, 2, 3, and 4. And these are the result of what? My simulations. Q1, 2, and 4 are in radians. Q3 is in meters, and of course Q3 can never go up that much. You know that, right? It has mechanical limitations. So here maybe I need to solve it for half a second or something, and really not for that long. Even in half a second it can go far up, right? You see here it is still too much, but in general, remember that this is how you can derive the equations of motion for SCARA, and you can You can look at your numerical solutions if you convert those symbolic ODEs into function handles. So most of the people told me that your examples that you solve in robotics are mostly, especially for the kinetics of the robots, not for kinematics, they're mostly the 2DOF robots. So can you go with a higher degree of freedom robot and get the equations of motion? Here we go. This is a SCARA with 4 degrees of freedom. So hopefully this was useful to you, and I will see you in my next lecture. Thank you.